Okay, everyone, on to day 6. Nothing new here today. What we're going to do is the theorems that you guys learned yesterday. Okay, the theorems we learned yesterday, you're going to apply to some more hardcore algebra problems. This is more like an honors level day. All right, I don't know if I do it in a regular geometry class, but honors level, definitely. So we're going to use all these theorems we learned the previous day and apply them to some hardcore algebra. You know, we're going to do some hardcore algebra because we got some friends back from Unit 8. We got law of sines and we got law of cosines. Okay, I can give you a little tip. We're not going to use law of cosines. We're just going to strictly stick with law of sines if we need it. We may not need it though. Okay, so the goal here for all these problems that we're about to do is make a triangle. All right, somehow use the theorems from yesterday to create a triangle. All right, if it's a right triangle, hey, maybe we can do a little Pythag. If it's not a right triangle, remember we got law of sines and law of cosines if we need it. All right, because those two, remember, can be used in any type of triangle. All right, so let's go to number 1. Let's see what we can do. So we see we're trying to find the length of the entire chord. We're given this little piece from C to the chord is 2. And let's stop right there. Do you see how that piece, I'll highlight it in yellow, that piece right there is perpendicular to the chord. And since it's coming from the center, it's got to be part of a diameter. And if you remember the theorem from yesterday, that a diameter perpendicular to a chord bisects the chord. So this chord is getting bisected, which would mean if I could find half of it, I could double it and find x. All right. Now you also see I'm given this piece I'm going to do in green, which is 3. Okay, and that piece is a length of 3. What is that piece? That piece is called the radius, which means any other radius you draw in that circle will also have a length of 3. Can you guys find another spot to draw a radius in that would help me out tremendously in this problem? Can you find another spot to put another radius that might help me out? And remember, we're trying to form triangles, okay? I'm hoping that you guys have selected maybe going this way. And that's also a length of 3. And look what I've just created. I'll draw it out here. We've created a right triangle where the hypotenuse is 3, one leg is 2, and I believe we could find the other leg. And remember, that's half of the full chord because the diameter bisects the chord. So now we can do a little Pythagorean theorem. 2 squared plus y squared equals 3 squared. Move everything over. Y squared should be equal to 5. So y is equal to the square root of 5. So that would mean x, I'm going to double it, is equal to 2 times that. And the directions do say nearest tenth, so I'm going to respect the directions. So you go to your calculator. What's going to be 2 square root 5? About, it says nearest tenth, so 4.5. Okay. There you go. So really, I use 2 circle theorems there. I use the diameter perpendicular to a chord bisects the chord, and I use any radii in the same circle are equal. All right, to get Pythagorean theorem. All right, not bad. All right, let's see what else you got for me. All right, let's look at this next one right here. I got 120 degrees for this arc measure is 120. I got a radius. Of 12. All right, I don't see a triangle yet, but I could make one here. Okay, I could make one. Is if I draw this other radius in, and what do we know about all radii in a circle? They have to be congruent, so that one also is going to be 12. So let me draw in the triangle I just created. I got 12, I got 12, I got x here. All right, but I know no angles yet. I know no angles, or do I? Or do I? Remember, this is the center right here, which would make this a central angle. And if you guys remember back to day 2, a central angle is always equal to its arc measure. And the arc measure is 120 there, so that angle's got to be $120. Okay, it's equal to its arc measure. All right, let's keep going here. Take a look here. I got 3 sides of the triangle. One's 12, the other's 12. I believe back in the day when we were together, we called this an isosceles triangle. And not only are 2 sides congruent, but 2 angles. So you guys could figure out those angles. Let's say I got 60 degrees left divided by 2. Each one of those angles is 30 degrees. Okay, can't do Pythag here. It's not a right triangle, but I can use law of sines. All right, which says if I take a side x over the opposite side or the opposite angle, sine of 120, coming back to you guys, equals, give me another side, 12 over the sine of the angle opposite, 30 degrees. Okay? So again, law of sines on any type of triangle. Now I cross multiply. So I get 12 times the sine of 120, x times the sine of 30. Divide both sides by the sine of 30. Again, also make sure you're in degree mode. Make sure that calculator, hit that mode. Make sure you're in degree mode. Okay, not too sure when the last time you used it. And if you're using the one on the Chromebook, it's probably in radians. All right, so make sure you're in degree mode, FYI. All right, and then you should be getting out nearest tenth about 20.8. All right, so using the law of sines with our circle theorem. Central angles equal to its arc. All radii in a circle are congruent. All right, let's go a little tougher now with number 3. Find the radius and the measure of arc AB to the nearest tenth. All right, well, let's work on the radius first. Okay, take a look at diagram number 3. If I draw the radius in, I could draw it anywhere, but probably want to form a right triangle, right? So here's what I have right now. I know this part was 5, trying to find the radius, which is the hypotenuse. Now, what about this missing length here? Notice the whole chord is 24. You can use the theorem that says if I have a diameter bisecting the chord, a diameter perpendicular to a chord, it bisects it. So that's got to be 12. All right, so for the radius, we're going to do Pythag. (25 plus 144 is equal to c squared. What do I have there? 220, 169 equal to c squared. So the radius should be 13. Okay, 13. All right, here you go. What's up next here? Now we got to find arc AB, measure of arc AB. And remember, since I'm looking for the measure, it's got to be in degrees. Okay, it's got to be in degrees. So let me start erasing some of this stuff so I got some room to work here. Okay, got to be in degrees. So let's see here. If I got to find that arc measure in degrees, all right. Is there any, let's see. What did we remember from, I have already gone over this today too, but from day 2, the measure of an arc is always equal to its central angle, right? All right, well, if I draw in that angle, take a look, angle ACB, everyone see that angle that's formed. So arc AB is going to be the same measure as angle ACB. Okay, an arc, all right, an arc measure is always equal to its central angle. So if I draw this triangle out now, ACB, so here's A, C, B. I know this is 24. I'm trying to find that angle measure right there. Okay, let's see. That was 5. All right, well, let's keep talking here. We just found the radius in the previous problem to be what? 13. And we got to find that whole angle there. Okay. Thoughts? Think about before we talk, because there's a bunch of different ways we could do it. Okay, a bunch of different ways. Trying to find that whole angle there. All right, got that. All right, well, what about this? All right, I'm trying not to bring in law of cosines because that is one way you could find that angle. This altitude here is splitting that angle in half. So if I could find one side of it and double it, you get the full angle. Okay, so let's take this right triangle right here. All right, I can still use law of sines here to find the angle. Watch. Give me a side and an angle that you know. 13 is across from what? The 90-degree angle. Okay. The angle I'm trying to find, x, half of it at least, is across from this side right there. And we know already that that 24 is breaking up into 12 and 12. So I can say 12 over sine x. Okay. I'll find what degree measure x is, and then I'm going to double it. And that'll be my central angle, which will also be my arc. So watch what I'm going to do it all in the calculator now. Okay, so I have 12 times sine 90 equals 12. Oh, that's fine. Divided by 13. I get that decimal. Now remember, that decimal is not my answer. You guys remember back in the day, 2 units ago, how I found an angle, what I needed to do on the calculator? Now that I know the sine of x is equal to that, I had to do the inverse of sine. Second sine, plug that decimal in, and then there's my angle. Okay, so my angle is 67.38013505, but remember, I got to double it, right? Because that's only half the angle. So I double it, and to the nearest tenth, it comes out to be about 134.8 degrees. Okay. All right, so that's a nice little way of doing that one. Okay. All right, you're going to pause the video. I'm going to pause the video, and we're going to try out number 5. All right, you're going to first find the radius to the nearest tenth. Okay, this 6 inches belongs to all of chord AB, so it's getting bisected. And then you guys are going to find the measure of arc AB. All right, pretty much using the same method we just used. Okay, so see what you can do. Pause that video, and we'll get back together here. Okay, let's see how you did. I'm getting 6.7 inches for the radius after doing Pythagorean Theorem. And then I am getting 53.1 degrees for angle ACB, which is also equal to the measure of arc AB, 53.1. If you're getting half that, remember you got to double it. Okay, and I still use law of sines, and I doubled that answer. Okay? All right, ask questions in the next Google Meet. If you didn't get that, we can figure out where you went wrong. All right, don't be bashful to ask questions. All right, might need a little moment of silence here. You may need to go grab a box of tissues right now, or we may just need to celebrate here. Let's just say, welcome back to our proofs. Welcome back, everybody. Beautiful, beautiful. All right, right off the bat, proving 2 triangles congruent. Let's do a quick review. You guys have 5 methods back in the day. We got side, 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 angle, side, angle, angle, side, angle, side, angle, and our good buddy HL can only be used in a right triangle. Okay? All right, so let's see what we got here. Arc AC and arc CB are congruent. All right, so if the arcs are congruent, we can use our tick marks there just like we would on a side. So now we need to get the two triangles congruent by one of our methods here. All right, so we got to go back to our theorems from yesterday. If the arcs are congruent, what else must be congruent? Okay, if the arcs are congruent, what else must be congruent? Well, there's a couple different ways we could go here. I'm just gonna go one way. If the arcs are congruent, that means the central angles are congruent. Angle AOC has to be congruent to COB. And our reason, all right, guys, what were you given? We were given congruent arcs. And what did we imply? That the congruent central angles. Okay, so that gives us an angle. Okay, where else can we go from here? Well, if you take a look, don't forget about this. This is huge. What are OA, OC, and OB in this diagram? What are OA and OB? They're all radii, right? So OA is congruent to OB in a circle. All radii are congruent. Okay, so congruent. And then we have our old buddy, can never go wrong. OC, congruent to OC. Reflexive. And then look at what method we have right now. We got a little side angle side action. Side angle side, okay? The other way we could have done it, if the arcs are congruent, so are the chords. So we could have said chord AC is congruent to chord CB and then done side, side, side. Okay, so that was another way around it. We could have done side, side, side as well if some of you guys were thinking about that. All right, another type here. Okay, in circle O, OC is perpendicular to EF. So we know if two things are perpendicular, they form right angles. Okay, a little something different. CFW congruent to CEW. So take a look at where those angles are. All right, and this goes back to when we were doing these proofs. You don't get those angles congruent unless I get the triangles congruent. Yep, this is a little CPCTC action. Love it. Little review here, CPCTC, but got to get the triangles congruent first. Okay, got to get the triangles congruent. All right, so let's do that first. Okay, because this radius is perpendicular to a chord, what's happening to the chord? Let me say it again. What's happening to the chord? It's getting bisected. So we need to write that OC bisects EF. All right. A diameter, and this is a long one, but it's useful. A diameter perpendicular to a chord bisects the chord. Okay? And what do we know about a bisector? Cuts a piece in half, right? So we know that EW is congruent to WF. Definition of a bisector. All right, quickly here before we move on. You cannot use that statement with that reason. The theorem says the chord is getting bisected. It doesn't say the two pieces are equal. All right, so you cannot use that statement with that reason at all. Okay, the theorem says the chord is getting bisected, so that's what I wrote in number 2. All right, what else can we have? Well, we got good old WC equal to itself, right? That's reflexive. And now the only thing we need to talk about is the old right angle that's in there. All right, remember the steps back in the day? We had to first say it was a right angle. So angle CWE and angle CWF are right angles. Perpendicular lines form right angles. And then, of course, right after we say they're right angles, we need to say they are congruent. So angle CWE is congruent to angle CWF. All right angles congruent. And we're almost done. Now I have enough to say the triangles are congruent. Just make sure we write them in the correct order as usual. So triangle CWE is congruent to CWF by side angle side. And then we can finish this bad boy off by saying now angle CFW is congruent to CEW, little thing we used to call CPCTC. Okay? Proofs aren't going to get any tougher right now than that. All right, so don't worry. All right, for now anyway. Okay, my big thing is you guys getting used to these theorems and facts and using them, whether it be in an algebra question or in a proof. Okay, just get used to these facts, all right, because unfortunately there's more to come. All right, good luck on packet pages 18 and 19. You guys know the deal. I'll see you at the next Google Meet and ask questions.